So we are just setting up before the tutorial, as you can see.
You can actually, while you're waiting, you can you can extract the zip file and upload it to your.
Yes, slowly. I will do that myself. But of course, you know how to do that. It's the same process as yesterday. Tuka has sent us the file. I hope you all received it through WhatsApp. I think it was. Tuka will be today the main person who runs the tutorial, because he has created the codes which we are going to be showing and the Jupyter notebook. It's going to be very similar to sort of yesterday's system. So welcome. Now we are going to do whatever I was telling you about this morning, in particular the Web2Weg embedding kind of LID, and I spoiled partly took us to show you the results. We could have been waiting until now and very excited, but I couldn't resist. I downloaded the GIAN embeddings which Tuka sent, and now I'm just going to upload it to my Google Drive. Folder upload, I guess. You must have done that, I guess, by now. You are faster than me. And download this one. Upload. Yes. Let's hope this is not going to take half an hour. So while this is uploading, then it's uploaded in the meantime, so I guess I can go there like you will and start the embedding analysis. Double click which one is this? The IPYNB file, and we get sort of our usual Jupyter notebook. As I said, I'm not sure whether I started saying, but I'm not sure whether we talked about it yesterday, but this Jupyter notebook sort of runs in this virtual environment, and it runs on the Google servers somewhere. So our machine is only sort of used as a display, essentially, as a client. So one thing is that it should be harmless. No code is actually running on your machine, really. And the other, of course, important thing, while this Jupyter is kind of handy, in particular for this type of purposes, is that the environment on the server has everything set up. As you know, many of you have the same experience that, setting up downloading some Python code from GitHub or something like that and sort of installing it and running it tend to be kind of painful process every now and then. There are all sort of dependencies which might not work on your machine. There are different versions of Python, different versions of libraries, and sometimes it's like painstakingly sort of complicated process. In particular, when you deal with the machine learning, there are all sort of interfaces between the GPUs and your machine. There are a couple of layers of interfaces, and that's setting something like that up, in particular for older codes, can be a real pain in some parts, body parts. So, but anyway, this is easy. That's a good thing. Jupyter Notebook also sort of allows to put all of this commentary. There is a code somewhere down here, but you can, for your convenience, you can kind of read the Tuka's sort of running commentary of the process whenever you want. There are some links to the papers and some pictures and all that.
Yeah. So. What I've already done kind of in advance is that I've extracted the embeddings from the Wave2Vec model, because exactly this thing that you have to use this PyTorch and all this stuff, and it'll take more time. But I'm gonna share that code as well with you later on another folder. So we're gonna go through these, what Jura has been talking today and the previous days as well, these different kind of visualizations of the embeddings, and I guess we have 2 hours, but it kind of represents work from quite a much longer time, like maybe a year or something. So let's see how, if I go too fast, it's difficult sometimes to know what people know when you've been working on something so much. Just please tell me to go slower or ask questions and just interrupt me. So this is kind of, so you can work this code on your own. Kind of everything that's going on is also in these comments. So especially on the kind of remote students, you can also kind of just go through them, kind of check out what's going on. But yeah, I think we should just go forward. This was just an introduction about how these things work, and Jura has already gone through that. But there's a couple of papers that you can check out, and also a link to the code to the Hugging Face API, where you can find the the model itself. So we've done the practical stuff. Does everyone have their environment sorted out? Looks good. Okay, so we'll just first mount the drive and import the Python libraries that we need for processing of visualization. This is exactly what we did yesterday, or what you did yesterday. It should take like half a minute maybe. Now it's actually, you can see here on the top right corner, it's connecting to the computer. So that's why it takes a little bit of time to start, because exactly, you're not doing it locally. And now you're connected to a computer. Okay, and now it's just to do it. And then you have to connect to your Google Drive like yesterday, because it needs the data from the other folder. Okay, so while we're waiting, so basically we're uploading 2 files at first. So we have this Assamese database that we've extracted the embeddings for, and also your own recordings. So the English and Indian language recordings. And we're gonna make kind of 4 subsets of the data. We have the Assamese, then we have one with both Indian and English recordings, and then we have one with only Indian, and then one with only English. So we can kind of see how they behave in that space, what kind of, maybe how they interact, these different languages. Okay, this is done, so we can go to the next one. And here we just, if you put the play, while it's running, I can quickly explain that basically we're reading the file, then we just scale it. So we take out the mean, we don't do anything, any other kind of normalization. So we just center the data with the standard scaler.
Already, so
yeah.
These are not recordings, the embeddings which we extracted before.
So these are 2048 dimensional embeddings. Each there's always one embedding per utterance. So each of you have, I guess, about 10 embeddings per language. And then we split the data into these different, we have one for English data frame, without English, we have Assamese, and then we have the English and Indian is the DF there. And we have about, what do we have, 568 audio files from you guys, and then we have about a little over 2,000 files from the Assamese data. And that was, I guess, from 6 different areas, a total of 2,000. And now we can actually here see I've printed the head of this data frame. So this is the Assamese data frame, and you can see that this is how it works, that you basically have this metadata on the left, you have dialect, then we have latitude and longitude. Longitude that I collected from Glottolog. You can access it. There's a languages CSV file. It's easy to get. Then you can just match it with the ISO code that you presented. And then you have gender, and then 2048 embeddings with a D as in dimension, D1 to D240, 048. And kind of having that D is there, I guess, so you won't accidentally start using these indexes. So it's not 1, 2, 3, 4, 5, because it's easy to forget to have some one letter in when you're searching the data frame, that you actually have a name for it.
Why all these the same?
There may be some bug.
3 dots here, so these are the vectors, 2048 dimensional vectors. Yeah, just list of 2048, 48 numbers.
But it's actually, let's keep that in mind for the actually important data, which is yours, that we don't have the same thing. So this seems that actually the same person has the same embedding. This can't be true, so there's some slight bug in the code probably. But let's just go to the next thing. So, so the idea is that if you have these raw embeddings, they kind of have all kinds of information. Exactly, for example, if some countries there's some languages there's some kind of imbalance of gender or whatever. So there can be, or if some, I don't know, room acoustics or some signal thing kind of affects the classification when it's trained the model itself. So there might be any kind of stuff because there's so many dimensions. So we actually want to see that what are the kind of most salient features regardless what they are. So we use PCA, which is a unsupervised transformation that can be used for dimensionality reduction, as Juraj said. And the idea is exactly that it only finds looks for where the kind of structures are, where the most information lies. So we do that. Now we only have 2 dimensions. We made it into 2 dimensions, so that's easy to visualize. And now if you play that, am I going too fast? Is everyone kind of following what's going on?
So, so I have a question. So, if the second step is your dimension reduction, right?
Yeah.
So that you have, is that feeding to the third step or not?
Yeah.
Yes. So if you go up. So I make this. I made a copy of the Assamese data, as in a PCA kind of data frame. I initialize the principal components analysis, and then I transform the data frame so that I only leave the first two principal components there. And next I will feed it into just the plotting, matplotlib plotting code. So now we want to look at gender. So let's see, as Juraj said earlier, this is something that might be quite easily there. So we just put column to color gender. This is something easy to change. If you want to later run the code again, you can check it out. Color with something else that's in there. In the Assamese data, there's not so many kind of different metadata variables, but in the Gian one we have state and city and all these kind of stuff that you can play around with. But so if you go up a little bit below, and if you run it on yours, it should look the same. So now it's colored by gender. So this is probably females and this is males. And it's completely separated in the PC space.
By the way, the important thing here is that the PCA is not aware of the gender. So it's only colored by gender, so the PCA is performed with completely unsupervised way of just turning the space in order to sort of magnify the dimensions along which the variance is the biggest. And now it's only post-colored by. So these are all the spots, all the dots, the positions of the dots, all come from a PCA. Then we just color them based on to what gender speaker that particular thing belongs. This seems to be the only number of speakers rather than number of utterances.
Yeah, it might be that
we already speak means. Yeah.
And that's probably that's probably why actually we have those rows. I've accidentally put one code where I've grouped it by, not grouped it actually, but made it basically that it's the same. So sorry for that, but it should be easy to fix. Yeah, so you can see that it actually splits with the gender. So I guess this is something that you probably know after Juraj's kind of lecture. But what is the problem with that? What might it? Do you think what does it tell about the model? Do you have some idea? That the first component splits the gender. So why do you think? What does this tell us about the model? That it separates the first component. So the most salient structural thing in the corpus is in the model. Basically, the model embeddings is gender. Yeah. So the training data. So probably in some languages there's only males or 99% males, and some languages not. And then it just thinks that actually the gender is the easiest way to kind of split this. So the LID model isn't necessarily that great. So we actually have to do something about it. So we have to get rid of that and just find the stuff that we're interested in, because we're not interested in splitting them by gender. We could use something.
So this is not we know that our data or the Assamese data are very well balanced. So this is not about the characteristics of the data which we are analyzing, but about the properties of the models, the language identification model which we used to extract these embeddings, which, as Tuka was saying, because it was trained on the data which was probably not balanced, gets this sort of gender bias and learned that gender actually is information worth keeping because it can assist it to decide on the languages. Or so it thinks, because that's was the characteristic of the data on which it was trained. Mm-hmm.
Yeah, so the original, the LID model that we used was trained with YouTube videos. So that also, of course, is very gendered, kind of gender imbalance is already probably there. So it's probably male dominated on its own.
And might also be might also be the sort of culture gender imbalance, that the YouTube videos from some languages might be more male dominated, the YouTube videos from other languages might be more female dominated, and then it turns out that it can use this type of very salient characteristics to decide on what language it is.
Okay. So we have
So,
to. Yeah.
Tuka, can we just take a pause and just make sure that everybody has followed all the steps and then they understand all the steps so far?
Yeah.
So I'll have to ask, so anybody who has not been able to do all the steps until now, everybody has done. Okay. And so everybody has understood what is happening until now. Anybody has not understood, please raise hand.
I have one small doubt. Do we understand which color denotes which gender? Here
In
is
this.
blue and red? Yeah.
Well,
Or is it undefined?
this time, yeah, it's actually undefined. I'm not sure, but doesn't really make a difference in this case. Of course, in
Yeah,
general,
yeah,
it would be
sure,
important. Yeah.
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 So I was just trying to read into the
Yeah.
code and see.
Oh yeah, yeah. I didn't make any difference now
Okay,
because
okay.
I just wanted to see.
So it
if
was random, right?
Yeah,
Just two
yeah,
clusters.
Yeah.
Okay.
They just happened to be kind of stereotypically gendered colors, but
Okay, yeah. Got it. Thank you.
There is this color map BWR which orders the colors. Usually blue is the first one and red is the second one in the standard color maps. So most likely blue is actually female and red is actually male because F is alphabetically before M. So most likely blue actually corresponds to female and red corresponds to male in this color map.
And if you like, we're going kind of so fast that the code itself, you probably won't have time to go into it so much, but all the lines have some comment that should kind of explain what's going on. The code itself is very kind of simple stuff. I understand that if you don't have any experience with coding, it might be difficult to at least quickly see what's going on, but you can do it, of course, afterwards as well. So yeah. Anyway, now we have I don't go so fast. So because this is separated by gender, we have to do something. We have to get rid of the gender, or we actually want to just look at the dialect in this case, or language, or whatever we are interested in. So now we get to this linear discriminant analysis, which I think Jura was also talking about. So now we actually don't do it unsupervised. We give it the classes. So it works similarly to PCA. So it looks for these directions in the space where there is kind of most separates the data, but they separate the classes. So then it tries to find where it's easy to see where different languages are kind of apart from each other and close to their own language, other speakers of their own language. So we actually do the exact same code. We just change the method here into LDA. So we make another copy of the original Assamese data and make an LDA data frame. We run the same thing but with linear discriminant analysis, also two components. So we just look at the kind of two most important dimensions for separating dialect. And if you run it, you again basically see that what's going on. There's the two columns. Yes, and we still have the same problem that they're the same, but doesn't matter. So let's go to the next one. So next we do, again, it's the same thing. We just look at the gender. We set it here on the first line that this is what we want to look at. And we see if they still separate. But now they don't. They are actually together. So it must be something else. Well, in this case, hopefully it works out that it's the dialect. And if you look at it's not randomly distributed. So you have this kind of some figures here. So you would expect that maybe some of these are starting to kind of lump some dialects together. Not necessarily really great because it's only 2 dimensions. It's kind of a small amount of information you have to pack into two variables. But it at least doesn't show gender anymore. So we've gotten rid of that. Is everyone kind of following until here?
This is a really sort of difficult step in some sense, because we just sort of turn the space so that what matters, what it tries to discriminate are those dialects. So, and not only tries to discriminate, to put the dialects as far as possible, because it knows what dialects they are, but also it tries to put the data from the same dialect as closely together as possible. And this doesn't do anything with the data embeddings. It just sort of turns the space in the right way. So the distances remain the same. It's just a different view of the space.
Yeah, and like LDA, of course, is a classifier, like mostly you can use it as a classifier. So you would have a training and evaluation set and this kind of stuff. But for this, it doesn't really matter because we're not interested in how good it is at classifying. We're only interested in the relationships, and it doesn't get any information about the relationship. It just gets the information. This is this class. This is this class, but it doesn't know that this dialect is similar as this one. That's only for kind of the structure of the data might bring that out. But I guess we can go to the next one. Okay. So of course that doesn't really tell us anything. We only have the gender. That's not very interesting. That's not what we're looking for. But we want to look at how the different dialects behave. So we just take all the utterances in Barpeta and all the utterances in some other place, and we take the mean of those embeddings for each dialect. Then we get one data point for each dialect in the space. So here I do it just on the first line, just grouping by dialect, taking the mean. So I get one row in the data set for that dialect, and it's the mean of that dialect. And once again, the column to color, later on you can change that, try something else. And later on we're going to also maybe do a little tweaking, but let's just get the kind of first few through, and let's get to your data, which is more interesting. So you can press the cell if you haven't to run it. And now we're getting this kind of a map of, or the space of those centroids. And we take the centroids from the already transformed LDA, linear discriminants. So we have this two-dimensional space with all the utterances. We just take the mean, so it's very, very, very simple. And we just put the two dimensions like this. So basically, this is kind of similar to the picture before, except we have specific one kind of blobs there, and it's not colored by gender. I don't know if you got through there, you can start maybe looking a little bit at if these make any sense. How does it look?
Well, we were looking at the same-ish picture earlier today, and we all concluded that it starts making sense.
Yeah. So what if you think about it, that you are putting 2000 dimensional information with 2000 dimensions into two, you're probably going to miss quite a lot, especially if there's kind of multi-dimensional kind of varied influences between the dialects, especially with languages. You definitely will have that. So it's not only this one retroflex or whatever that is kind of the difference, but there's going to be a massive amount of things. So 2 dimensions is very little. So I don't know about this, but with the word languages, we noticed that it actually made this east-west kind of continuum, but the kind of minute details were not at all right. They were complete gibberish, but the kind of overall continuum was good. So of course we can also do LDA with more dimensions and not filter into 2. So with LDA you can do the number of classes minus 1. So if we have 60 classes, it will be, I don't remember how many classes we have, but let's say we have some tens of classes. So we can look at if it becomes better if we don't make such a bottleneck for the information.
Of course, the issue, the thing is that we have all the information ready. We're only extracting the first 2 components for the visualization purposes. That's all there is to it. Like we can extract 50 components, but then we are in the same sort of problem that we cannot really visualize that. But there is much more information, of course, kept in the embeddings. All of those means and all of those things, those centroids, the means of multiple vectors are all done on all the accessible dimensions. We are kind of using the 2 only for the visualization purely.
We'll go to the next one.
Of course, the code stays with you, so you can play with that and change things, But because it's running on the servers, you cannot really break anything, and you will not break Google servers. That's for sure. So it's pretty safe to the only problem is that it might not work when you change something, but that's fine. And of course, when you are interested, maybe not tonight or tomorrow, but when you sort of want to kind of think about this even further, you can maybe look at the slides from the lectures and compare them with these steps to try to sort of understand what I tried to say and how does that translate to the code. That might be sort of useful potentially.
Okay, yeah. So this first thing was just to show you kind of how it works with the Assamese data to and maybe compare in a moment a little bit how your data works. So we have already extracted the embeddings, as I said, from your data, from the LID model, and we merged them into this Gian embeddings file. And you can take a look later there what kind of stuff is there, and we'll see here as well. So you can just put that. We'll do the same PCA, but for your data. So now we have actually a little bit more metadata that we can use. We have the language, we have the area, and then we have the latitude, longitude of the language you are speaking, and then we have also home latitude, home longitudes for the English recordings. So then we can check out how those English recordings seem on a map. We have the speaker, we have the mother tongue, city, state, gender, age, and then actually now the bug is not anymore there, so actually this is good. This works out. And we have 2 dimensions already because we've done the PCA here. And actually on the right you can see pred label. This is something that's kind of semi-accidentally here, but it's actually good. That is the prediction of the model itself. So in this case it has predicted it right. BN is some kind of other ISO code, other set of ISO codes. So it has predicted all of these utterances as Bengali. And we can go further. So we'll just do exactly the same thing as before, now with your data. And we'll do it with gender. But this time, it's not mixed. And I have been trying to a little bit think about this. I have actually no idea why in this case it isn't mixed. If you do, feel free to loudly say your ideas, but I think it's a bit kind of difficult question. Then in some cases gender is there, sometimes not. Of course in this case these are very kind of much more different languages from each other, like they're not dialects, they are very kind of the space is kind of maybe more varied, so that might be one reason that it would be within dialects it might be that it's kind of more shows more, I don't know.
On the other hand, then we got the quite a relatively strong gender separation on the world languages as well. So
true.
And and thirdly, I would have guessed that we will get even bigger gender split because we have extremely unbalanced data which we're analyzing. So maybe somehow we would have to think, this is difficult to think because you have to imagine these transformations somehow. But you know that somehow that gender imbalance in our data somehow compensates for the gender imbalance of the or gender bias of the network language education. But yeah, it's a mystery.
Of course, there's always now this is stuff that we made the corpus day before yesterday, so there's always kind of room for some bugs or some kind of other stuff happening which isn't which doesn't have to do with the real world, but it's just an interesting thing that it actually does this. That actually we could maybe even just use the PCA and leave out LDA completely, and we can see about that in a bit. But let's first at least do the same thing that we did with the Assamese stuff. So let's do the LDA. And actually, just before we go, I made the LDA with, just a second, sorry. Oh no, nothing. Yeah, that's all right. Yeah, we can just go further. Yeah, so we made the linear discriminant space now, and we'll color with gender. Okay. Now it also looks quite different from the one that we saw before. And now they actually, it seems that there are these kind of very specific blobs, perhaps languages. So they're not like this kind of scatter around, like kind of overlapping as it was with the dialects, but they are kind of very specific kind of places. But then this gender is still maybe a little bit doing this kind of thing. Like here you have something that's very similar to each other, and like there are like this little bunch of one gender and a little bunch of another. Do you have any idea why this might be the case, that we're using LDA, so we're using the languages as classes, but we see this, that the gender is actually maybe separating a little bit? Do you have some idea what that tells about our corpus that we made compared to the Assamese corpus?
I didn't get the question.
So, when we looked at the Assamese corpus, we did the LDA and it mixed the genders. So you don't anymore separate them at all because it only looks at dialect. We did the same thing with the languages, with your data, but it doesn't do that. It actually, well, it does it in a lot of cases. Here you have mixed gender. This language is mixed, but these are like here. So you have a little bit of separation of gender as well. So that says something about you guys who have given it. Do you have an idea what that is? Yeah, so we might only have one person from one language, and that is a female. And then if you start separating languages, it's of course going to find that thing about that language. It's not going to find the kind of language differences. It's going to find the idiosyncrasies between people or gender or whatever. So this is like stuff that a lot of our work kind of delves with, is like figuring out why does this seem good? Is it really like something that has to do with the language, or is it this kind of massive amount of variation that can affect these things in the models? Because they take everything from the signal. It can be that it's some little noise somewhere that it's in different recordings, and it only takes that. And that has been the case with some dialect identification work.
Just reinstating what Tuka said, that a lot of this work using the machine learning methods, is to run these codes and design these things is actually relatively easy. But to really convince yourself and the others that you are tapping on the right source of variation is very, very important. And it's very good to have a very skeptical mind. Like we had several anecdotes about, remember the Swedish data processing, many imbalancing in the corpora. And this comes from our experience when we had several Eureka moments when we really went back from home, from work, kind of excited that we found something really important, and we realized that it's some microphone characteristics and things like that. So there is a lot of history, not only in our group, but overall in the field, that people publish stuff which turned out to be completely trivial, and a machine sort of learned to distinguish sounds based on some hum of some ventilator somewhere, as opposed to or you know, different things from different languages based on actually the frequency of the current in the different countries and many of the other things. So we have to be very, very, very skeptical, in particular when we are starting getting very convincing results, that we are really tapping that source of variation we claim that we are tapping. Because there might be many correlates. You know, people in different parts. I'm not saying that this will come to the recordings. It will not. But you know, people in different countries drive on a different sides of the road. So we might use some particular, you know, recognition of something which taps on this coincidental, confounding factor. This is not enough to can reiterate this all the time, because as I said, it's easy to find some results and it's much more difficult to justify them. So, and that takes way more time. I think we got these results about a year ago, and it took us almost a year to get them to publishing, because we had so many doubts, and we had sort of quadruple checked every step whether we're actually getting what we claim that we are getting.
All right, let's go to the next thing. So we'll just do the same thing with your data as we did with the previous one. So we'll just get the centroids, the means of all the utterances from that language, and we'll see what the first two LDA linear discriminations show. And once again, you can maybe think about a little bit, does that make any sense? Is this same as before? You guys were talking about the retroflex. Hindi is here in the middle, kind of there's the purple thing. And just one thing is that, so I think someone was talking about Bengali, that it's kind of in the wrong place before. I'm not sure, but anyway, if it doesn't have any kind of close friends, it's going to go next to something. So if there's nothing that is very similar to Bengali, it might find something similar in a kind of far away, and then it'll seem a bit weird maybe. I'm not sure if this is the case with Bengali, but this is something that happens kind of often when basically missing a language might make a big difference in the kind of structure of the tree, for example. Yeah.
Yeah, I was just gonna say that, and also we have to remember, probably, correct me if I'm wrong, that we are simply basing it based on how it sounds like.
Yeah. Yes.
Right.
Exactly.
Solely based on how it sounds
Solely
like. Yeah.
based on-
So probably it often is more about geographic proximity, less about language family.
We haven't, in our data, we haven't really looked at dialectal variation or anything of the sort. But it could be that is what is affecting the distribution of this data, right? Because we have a very small number of speakers, and they are, at least I know from the Bengali data, I don't really know for the other things, but like those, like very small number of speakers are spread around in quite a few places. So all of their data is going to be quite different.
Yeah.
So that's probably affecting how it's being plotted, right?
That's a really good point, and that's kind of, I think, the reason why Jura talked about this kind of that we need like 50 recordings to get it kind of robust, and it's not really, I guess, that you can get it perfect with one recording, of course, because it can usually, like, the classification rate is super good. It can get it right on one, but of course there's so much this within language variation that if you get 10 people from Western Slovakia and 10 people from Eastern Slovakia, they're going to cluster with, these two groups are going to cluster with different languages because they don't sound like exactly the same. So yeah, exactly, that's why I think the kind of benefit of this is we don't need specifically 1 or 5 representative speakers, but we can actually get a lot, and then we get some sort of a representation of let's say some area or language. Of course, in the case of language, it's quite difficult because they are quite elusive.
Of course, one thing which we could try, I don't know whether you tried it, is to actually not to get the centroids for the languages, but get all the speakers and color them by the languages, and see, oops.
You will do that later today.
Yeah, we will do that later today. So we will see. Also, the one other thing is that if I remember well in the database, Bengali and Hindi and Assamese. Bengali, Hindi and Assamese are the biggest speakers groups. So the LDA might have, because these are the biggest groups, LDA might have tried to push them as far as possible from each other, because it was rewarded for pushing these big groups far away. And one Marathi speaker didn't matter so much, so it created this basic geometry by pushing these overrepresented categories, overrepresented classes far apart. That might also be the case. Yeah. And then organized all the others sort of as good as it could to be kind of close to the similar sounding languages, but the major sort of diagonal is these 3 languages.
And actually, we might not have to do it now because there are quite a few things that we want to do, but if you go a little bit up, so here when I made the LDA, I actually made a PCA one as well. So we do have that data now both in LDA and PCA, so if we go a little bit down again, here, so there's the comment on the middle, so it says here, delete the hashtag from the line below if you want to see what dendrogram looks like with PCA space. If you just take that out, and run it again, you'll see the PCA of the PCA version of that kind of map. So this is what it looks like without the LDA.
Wait a second, has it finished?
It is? Oh, let's see. Come to corner PCA. It might be on the... So, I did this today. If you move that line a little bit up, so after the...
We have to
uploading
here, yeah.
I'm sorry. This was a very late kind of thought that I wanted to add. So you can put here.
LDA here.
There's but there's here as well in the bottom. I think it's maybe better not to put it now. It isn't that important thing, but you can maybe on your own. I'm gonna repost these into one kind of you're gonna get all the materials on one kind of a Google Drive, and then that'll be kind of the final thing. So I'll fix that before that.
Can you just repeat what the problem was
So-
on showing that
so that it-
specifically the online participants?
Yeah, so the
So
idea
just-
was that I wanted to, we would have, just if you comment out the column to color thing, it would show the PCA version of this, but there's actually, in the plottings itself, I forgot to change a few, in the scatter kind of line that you went away from that, but anyway, it should have been a different data frame that we are referring to, but I will fix that, so let's just forget that ever happened.
Segment and replace.
Hmm?
Can we just select that segment and replace
Sure.
that because it's just some parts.
If you want to see it, yeah,
not-
sure, I can do it if you,
Say again, sorry.
so take out the, so all the,
All the
All these
LDAs
have-
should be feed. That's what I was checking. How they call the
Yeah.
PCA.
yeah, you just say change those to PCA.
Yeah, but I'm just was checking. That's what I was.
Oh, we will
scrolling
have
up.
to change them back probably. No, actually we don't. Okay. Yeah.
Let's just first plot this. We're gonna get the
But you put it.
labels in the wrong place. It doesn't really matter. No, but that's what I mean. It's not called PCA. That's what I was looking for.
No. It's
Call
go back. Wait. Stop. PCA.
it- they don't
G on
exist.
mean PCA DVAF.
Hmm?
You put G on in the before it. So
Yeah.
PLT scatter G on.
Like that.
G on.
Yeah.
How
I
does it work?
cannot enlarge mine actually. Funnily enough.
How does it work?
I can look.
Ah, you can do it. Okay.
Like this is the name, yeah.
Yeah.
That was I was scrolling up. I was looking for the name.
You have to put the annotate as well. Yeah. Thank you. There's one more. Okay.
Uh-huh.
Let's see if that works. Okay. No? Is it still the same?
No.
Okay. Good. Okay. Oh yeah, now Assamese and Bengali are there. Okay. But actually, does the top there, does that make sense now?
It does.
Yeah, it does.
Yeah. So I guess in this case, the PCA on its own actually works somewhat well. So they might not even need the LDA. What is it? There's something really weird going on there.
But here in the sorry, here you have English.
Yeah.
Why you didn't have it in the other one?
My
Okay. But yes, this is just to show that. Oh yes, go ahead.
Why is this difference happening? Because after applying LDA, that F naught is getting removed, right? I mean, it won't be looking at the characters which are distinguishing the gender, just
Yeah.
focusing on the district. So it should work better when LDA is applied, but it's working better when PC is there in case of SMEs and Bengali.
I
Why
think
is it happening?
I guess in this case, I don't know why it's happening, but of course now that we looked at the PCA space, then in the Assamese data it did separate, but in this one it didn't. So it looked quite good without LDA, and the LDA might even kind of do bad exactly because of this really bad imbalance of our data set. So it might make it more kind of gender biased if you use the LDA because the gender is so heavily connected to language in this data set.
So essentially, LDA does not has anything gender characteristic removing from the thing. What it tries to do is to separate what it believes are the classes, in our case the languages, as far as possible from each other. But if in our database, as we well known, there is a hugely strong correlation between the classes, the languages, and the gender. What it does, it sort of pushes the genders apart. Because if the one language is only recorded by females and the other language only recorded by males, then it goes like, oh, I got what they want to do, they want to separate these classes, therefore I pick the gender as one of the characteristics which is used actually to push them apart. So we might actually now, if we have the heavily imbalanced corpus like this, by applying LDA we might actually be imposing gender balance rather than removing it.
The reason why I'm confused is because, for languages like Assamese, Bengali and Hindi, and I think Bhojpuri too, words might be very similar, Chand Hawa, and like translation of north wind and the sun. So, it won't, but at least they will be closer than other languages.
But
Like
this
for-
probably doesn't grasp anything about kind of word similarity.
No, I mean, then whatever features, for instance, Bengali and Assamese have similar features. Like they should be closer,
Maybe-
right? Even.
maybe the whole
Sure, sir.
maybe the whole idea of closeness is very different, because the reason being is that if I just when you said it, I looked into the string of first 10 words, and first 10 phonemes, they don't just uttara botahar belir majat. That is what, and then Bengali it is said uttara hawa ar shurjor shurjo, something of that sort, right? So again shurjo belly, hawa botah. So possibly, like, that is making a difference.
And also we are really looking way more into sort of phonetic and prosodic similarities. That's how this pipeline is designed. Then I don't. It's hard to say whether the sort of language classification thing really is capable of. These are for these type of networks which really process the files on 25 millisecond level to start with. Of course, then it gets summarized and all that. It's quite difficult to really learn. The word is a very long event in 25 millisecond steps. So it might not be really learning these type of. It might learn some very repetitive things like morphemes. If there are some morphemes which repeat very often, there might be small chunks of speech, and they are somehow very characteristic about the language, it will probably learn to capture those. But words are very long events for this type of processing.
And also we can be somewhat sure that whatever they're saying specifically in this case, it won't make a difference, because we're taking all of the sentences and an average of those. So of course the specific start, for example, makes no difference, because you have kind of 10 sentences there, kind of average, the kind of what Jura was saying, the pooled embedding, and you get average of that. So it should kind of, even with the, it shouldn't really grasp much more than maybe exactly what is common in that language. Does it often do this the thing? Not specifically that. And that's what we're kind of happy about, I guess, is that we don't have to have these specific sentences as you often have to have, like a very controlled corpus. You can have many kind of random stuff. But yeah, let's just see now that what happens if we actually get some more stuff. Let's go back up and change back that just to the. If you can comment out again the column to color. No, you don't have to change that. That's fine. We're not going to use those rows anymore. So just the column to color. No, not that one. I'm sorry. There's two of them. So the one below the information that's deleting the hashtag. Just comment it out and run it again, because I'm not 100% sure if we're using that again. And then let's go to the next one. Okay. So now I think I referred to it earlier that using the 2 dimensions is not that helpful. I mean, it's helpful, but it only gives the kind of broad overall stuff. Now we're going to use all the dimensions that we can in the LDA. So number of classes -1. So in this case, I think it's 12 or 13.
They're running without English. What does that mean? They're running without English something?
Where? Yeah. So this is without English, and I'll let you know in a moment why. But now we only have the Indian language sentences, and let's run it. And now we have about 12 dimensions, and let's just run the next one, because this is exactly what we already did. And if you go a little bit up, I remember what I'm going to say. Yeah. Right. This was just basically what I think has already been kind of discussed a little bit. This hierarchical agglomerative clustering. And let's see what it looks like. So now we don't have English.
Remember that we have to be, with this database, we have to really be quite a glass half full type of people, because this is astonishing that we get anything from that. If you imagine we are doing typology on that little corpus we recorded,
And also it's actually right now, it's fine if it's bad. I mean, it's fine if it's bad always, but we're going to see something that hopefully might make it better, which accidentally I found out. Just keep in mind if this is okay or not, whatever, kind of how well it works out. And let's see if we add the English ones. So if we think about it, that our data set is really heavily biased on gender, and we do this LDA and it pushes all this stuff out, but all of you have recorded English as well. So if we add the English there, it can't really, to the same extent, it can't use these kind of peculiarities and this gender-based stuff, because all of your data is also in English and has to be pulled out to its own thing. So hopefully that actually might filter the gender information a little bit.
Also, it's the biggest class, and LDA is a classifier, so it's sort of awarded for doing good on the bigger classes, and it's the biggest class, so it really tries to put all the English recordings together, because that's a good thing, you know, because it's told to put them together. So whatever else happens, it tries to put the English recordings together. Shall I run it?
Yeah. So let's see. This is again almost as exciting for me. Okay, let's see. That's the next one. So now we're making the same linkage matrix, but with English. And if you remember how it was, is this any better? It is? Okay, good. That's why I kind of thought that it actually does help that we put all of your English recordings there.
Is this split about the retroflex here?
Okay, okay, yeah.
So these would be the languages containing retroflex. Now, for the people I don't know, you can see, I guess, my mouth, even online people. And these would be languages, including English, as a matter of fact, which do not contain retroflex, I guess. Of course, English is on this left side, but that's another thing kind of to every nowadays remember when we are interpreting these dendrograms, that English could also be on the other side. The split is important. The positioning, whether it's left to the right, makes no difference. This is a good coincidence that it ends up there.
Okay, so of course, yeah, now we have done this tree. I guess with a lot of languages, if you're going to do a poster or whatever at a conference, they won't have no idea where these languages are, so it's going to be very difficult to show a tree. So let's just try putting it on a map. So what we can do is to this linkage, so this is where we get the tree, the agglomerative clustering. You can tell it which kind of level do you want to extract the clusters. So you can say that I want the point where you have 5 clusters, and then get that information out, which language is in which cluster, or which speaker, or which utterance, it doesn't really matter. And now we have put 5 is the one that we have put here. So we put n clusters 5. You can change that, you can run that a few times and see kind of the different what it looks like. Of course, you guys, you don't really need it as much because you know where these places are. But even if for like me, when I'm doing Finnish, it actually helps a little bit because it's hard to remember when you look at this, like the whole kind of big picture. So if we just run the 5 one, we can see where they go. So on the level of 5, it actually geographically looks good in a way that there's no random ones in the wrong place. So it actually makes these divisions. And often, like, if you think about...
So I guess these are the North Indian languages, like Gujarati, Hindi, and I don't know. And these are the South Indian languages, plus Bengali. And this is Assamese, and I guess this was the Angami, Naga, which clusters with them. And these are all the other northeastern languages. Super cool.
Yeah, and often, like, when we did our world languages paper, that kind of...
English.
Yeah. World languages paper that this geographical distance is really important, but you don't really know where to put the dot. For example, now here, maybe this is not the place where this person is, so this is just where the glottolog put it, because it's the kind of some ISO code puts the dot of Bengali there. So you could put it here or wherever, like the whole area where that's spoken. And often, like, for example, what is kind of near languages? Like, I mean, Russian, you would put it in Moscow. So that's quite near, you know, Finland or near Eastern Europe. But Russian is also spoken next to Japan. So you could put it there. So it's kind of difficult to say. And for example, there's mountains, there's areas where it may be actually some driving distance, or maybe, I don't know, distance 500 years ago, how long it would take, where the roads were, would be actually a much better kind of a metric, which kind of places are close to each other. So for example here, if you look at that these green blobs, if you go a little bit further.
I just wanted to make the same point as you, that, you know, this is your English recordings, and it's geographically put in London.
Yeah. So for example here you have on the right, you have the blue ones and the green ones and the gray ones. That could be that it's kind of less traversed. There's maybe been less kind of commercial routes or whatever. I don't know if that's the case, but that's often with ours. So, for example, in the Caucasus Mountains, there's kind of ones that are very close to each other physically, but they're not very easy to terrain to kind of cross some mountains or something. So that might be not necessarily in this case, but like kind of stuff that is, I think, interesting to see, like where these languages get these kind of, where do they stop sounding similar, even though they might be very closely related languages.
But I guess in this particular case, it's the sort of a little bit other way around. That the one outlier is that this particular Angami Naga is actually not green, because this is a very different language family, of course. These are, I guess, all the Tibeto-Burman languages, so they are sort of not related in any sort of meaningful way. But of course, it's also interesting that it's the sort of Angami speakers here who, this is based on two people, I guess, who, I don't know, maybe you speak Nagamese often enough or something like that, and something, maybe if you re-recorded the data once again and back in Jotsama, it would sort of sound different.
Yeah, that's what I was saying, that basically these are just from the Goto log, so we haven't put the coordinates ourselves at all. They just put so not our fault.
So it should be probably somewhere.
Yeah, that's what I was saying earlier. That basically this is exactly the thing that you always put, like Finnish is always in Oulu, which is a kind of a strange place in northern Finland. I don't know why they put it there. It's not in Helsinki. Russian is in Moscow, and then some other languages. So they are. I don't know who put this.
Yeah. And English is in London.
Yeah.
Even Australian English is in London, as a matter of fact.
But yeah, let's see the next one.
There is somebody decided in this big database the language, and they put these coordinates somewhere. And of course, they did as good a job as they could, but that's just random thing.
Yeah.
I'm sure that there would be different databases where we can get different things.
And of course, you can manually change these, but I guess especially when you have a lot of languages, it's easy to get from a kind of database that you can kind of compare to other people as well. And that's why also the language names are weird. The individual language means that there's a macro language of that same language in the Glottolog database. So there's another ISO code for the macro language. There's one that said India or something in brackets, I think, and that's because it's spoken somewhere else, and it has a different ISO code there. But for Bengal, there's no different ISO code. I guess it's only for one. There's only one variety in the Glottolog. Okay, so we're gonna do the same thing now. Take out the Indian languages and let's see how they cluster, how your Englishes cluster. So that would be kind of interesting because you're saying the exact same thing. So that cannot be anything use basically what you're saying. And we should expect that it's probably worse. So now we have the maximum amount of dimensions with the LDA, and let's run the next one. And now we color with mother tongue. So whatever you set as your mother tongue is the one we color, and where we will put the map in a moment. So here, let's see what happens. So this is much worse, right?
I think it's pretty good.
Well, Malayalam and so it can even.
In particular, if we take our Gujarati speaker who is not here, who admitted that her Gujarati that Assamese is better than her Gujarati by now.
But this is actually interesting as well. That it might be that the model would classify your English as your mother tongue, not English. At least that's been the case. I think who trained this, they checked it out, and it actually doesn't really understand these world languages. With English, it might not be the case because it probably might have English recordings in different kind of varieties. But with a lot of languages, I think that the thing is that they only have the kind of standard European variety, and then it always classifies it as like African French as some Congo language, like Congolese language. And that's probably why it's quite good at this, that it actually grasps the mother tongue, because it doesn't. And actually, as a phonetician, I guess this is a really good thing that this is what it does. It doesn't have words there. It's just how it sounds.
There's one remark we often sort of discuss, which we forgot to mention, that we are using classifiers here every now and then. Essentially, the language identification model was trained as a classifier, you know, what language this comes from. LDA itself is a classifier, so we're actually combining classifier on several layers. But interestingly, what we are relying on is that the classifiers are imperfect. If these classifiers, if the LID model was perfect and separated all the languages far apart, we would not be able to do this. We are sort of richly exploring or exploiting the imperfections of the classifier. Both actually, in particular the LID classifier. If the LID classifier was 100% perfect, it would split the languages far apart, it would always guess the things right, we would not be able to do this type of analysis. So we are sort of exploring the areas which are difficult for the classifier in some sense. So it's kind of interesting that even after all of that training with all of that huge amount of data, it's a difficult task, and that's why we can actually, you know, use this type of classifiers we use essentially the uncertainty in order to explore the data, where it makes sort of mistakes, which languages actually can mix up. That part essentially we are using here.
So I think next one is the final one of this, and then we'll let you.
Super impressed with this.
Then we will let you kind of play around a bit more on your own data, but let's just look at the kind of how it works out with your Englishes. And remember, you can on your own computer you can change the number of clusters and rerun it and see how it works out. But yeah, it seems it's more random, I guess, but it still has some sort of structure. Of course, it would be easy to say if there were a lot more languages or a lot more a lot more speakers and a lot more areas. But yeah, perhaps there's something there. Although the South Indian languages would, well, it might, but not. It's not great, but it's I guess not the worst. So
again, of course, this is kind of you know, and you might, of course, you all learned English as native language, most of you, but you have been also using the English to communicate in Assam in the last maybe 5, 6, 7 years. So your English might be influenced also, unlike maybe your mother tongue, your English might be influenced also by the communication around here. You might sound more like, you know, I lived in Ireland for many years, and when I left Ireland I sounded like Irish. Now I certainly don't, although some people recognize it, but you know, I might sound like a Slovak or like a Finn. So for me at least, but I'm of course unlike I'm non-native speaker, it sort of changes. So it changes with the people you communicate. So this is really super difficult task to judge this on the data we are actually using for it. I'm still astonished that it works to this extent.
yeah, I guess this shouldn't work at all. Of course, like it should just think it's all English and you know not have.
And essentially, here these East, Northeast languages are all perfectly fine. They're up to 2 clusters, but they are all separated from the rest, which is amazing.
So I think this was actually if you go a little bit down, I think this was the last picture of this Jupyter notebook. Yeah, so now we've made these kind of few different, you've seen kind of various ways of processing the data, and you can do that on your own. You can of course also plug in your own data. You can get any kind of corpus, and you can, like, I'll give you the code for the extraction, and then you can just put it there and run it again and change whatever you want there. You can exactly for the, can you go back actually? For the maps, for example, I think it might be interesting to look at the cities where you are from, and then see how those actually cluster together. For example, do different cities in I don't know, Assam, for example, cluster together in the whole of India. Actually, just something that I was what kind of just came to my mind is that, of course, this is all like, this has nothing to do with prosody, or I mean, probably has, but it's not like a prosodic thing. Or in general, like phonetics, we don't really know at all. We're just playing with this data. But of course, what good thing is that apart from maybe learning something new about how these kind of languages affect each other, how they change and stuff, but it's also for kind of creating questions that you can really quickly do these things. You can find out, for example, this like I don't know, this English thing that I just put. This was just a random thing that came into our minds in one meeting, and then you can get some hypotheses and try it out. And if it works out, then you can of course also do the kind of painstaking phonetics kind of study on that. You can get the kind of what you want to study. You can find that thing that, okay, this is interesting, and then you can actually do some more kind of traditional stuff on top as well. Let's look at the TensorFlow, I guess. So next, I won't show you anything, but you can work on your data a little bit more, and you can actually check out where your own utterance is, and kind of all the different kind of variables you can look at, and different kind of transformation techniques. I won't go through them, but it's so easy to look at. You can just see how they kind of work out. And there's three different, there's PCA, TSNE, and UMAP. And of course you can read about them and how they work. I don't really know how they work, most of them. But if you go to projector.tensorflow.org, in the zip that I shared you can just go to the whatever you extracted from there. In the data folder, it should have one file called.
What is this one?
Yeah. Found it. Yes, exactly. So on your local computer, there's a Gian projector embeddings. You should put that on the top one. So you go to the load on the left. There's some instructions on the if you go to the embedding analysis. Here. Okay. So there's a picture here. So you can kind of look back to it while we were looking at them. So there's you have the dimensional reduction, you have the labels that you want. So you can label the dots with whatever you want, and you can also color them whatever you want.
But maybe we just show it,
yeah.
and then we can do that. So
yeah.
I load these projector embeddings,
and then the metadata.
And the projector metadata here. This is super useful tool. Like we've been using this all the time. All of these other projections only come after using projector. We actually have our own offline implementation of that. So this is super useful. Like if you want to kind of use this type of analysis and visualization, you can set this on your home page essentially. This is super cool.
Should we do a break now?
Yeah, actually that's a good idea.
In a minute. Let's just literally 2 seconds finishing that, and then everybody can play with it and explore. Mm-hmm.
Yeah.
So here we now loaded. These are probably all the data from, I don't know, everything. Yeah, these are individual these are individual sentences.
Yeah. So you can put speaker, for example, and then you can
color by speaker. So we have 37 participants. So these are your different sentences. We color it by mother tongue. You can see that already, and this is a 3D as opposed to 2D, so we can turn it around. You can see that already the clouds are becoming visible there, and then there are multiple other visualization, of course I can only put it in a 2D. We can see the clouds here clearly. I just uncommented the third component, and then there are these other crazy dimensionality reduction techniques which do all sort of cute things. I wanted to say that if you didn't play with it, you cannot break anything, but that's not completely true. You will not break your computer, of course, or you will not break TensorFlow, but sometimes it gets sort of glitchy, so we just reload it. That's what you need to do. I'm looking here at the embeddings from the 3D space, 3D PC space, and if you look at them, there are these three big clouds. If you click, by the way, at any of these dots, it will give you whatever the dots is about, Asami, speaker, Tinsukia, and all that. So these brown, I have it colored by language. So this brown cloud here, it's on my screen at least, it's Assamese. This blue cloud here is Bengali. This red cloud here is English. So it's a big one because it's sort of what same amount of as the everybody else. And down here is Manipuri. So these are, I cannot find Hindi anywhere. Is it Hindi? Yeah, Hindi is somewhere here in the middle. But I guess, so when I'm turning this 3D, if we had the 3D thing, the turning, it sort of roughly corresponds to the PC analysis. You know, if I remove the third component, I get the PC, only the two principal components. So it sort of corresponds of turning this 3D picture so that, you know, I can see the biggest spread. It's interesting here, I'm looking at the sort of Nagaland mystery, and these orange dots here are the Angami Naga. You can see that they actually do indeed, by and large, cluster with the other sort of Tibeto-Burman languages. Some of them are deeply here, next to, I don't know, well, this is Malayalam, but yeah, but they are sort of a little bit in this space, in particular in 2D space, sort of closer to the Assamese than the others. But of course they are spread, so it depends on who you take. So this is of course with a small data, it's very speaker dependent, you know, or very one particular outlier already pushes something in, you know. It's kind of we seem to have two speakers, yeah. But these are of course only 3 dimensions now. If we take, this doesn't have LDA by the way. If you press this A here, you can get the labels, but they're very, very small. You can here choose which components we put. You can see that the first component actually explains 17% of the variance, whatever it means, and the others sort of add very little. So if we take third, fourth, and fifth, the things start getting a little bit mixed up, but there are still more information in the further dimension by the look of it. It still splits things by languages. By the way, this projector, TensorFlow projector, was designed directly to visualize embeddings. You can plug this to your TensorFlow based deep learning thing, and it can actually visualize the embeddings on the run. As you are training the system, it can sort of show you what are the embeddings doing. When I told you that these embeddings sort of are trained first, that's how we found out that we used the sort of TensorFlow version of this projector, and we saw how the very early on, after 3 epochs, the embeddings sort of spread around, although the performance of the synthesizer as such was still relatively poor, but the embeddings really spread quite quickly. So that's how you can see that whether for your application, the embeddings are really training fast. Unlike these, there are the other visualization things. So unlike actually PCA and LDA, these other TSNE and UMAP projections, they actually do move the data. So they are at just a SID where they are projecting the data from the whatever 500 dimensions, so 1000 dimensions here, 2000 dimensions here, to 3 dimensions, but they are creating this sort of creative way of projecting by literally finding the place so that the distances in this 3-dimensional space are as similar overall as the distances in much bigger space. So they are essentially creating the new way of distributing the points in a 3D space so that, yeah, that the distances are somehow maintained. And as you can see, TSN is doing it iteratively, so it keeps moving for quite a while. Sometimes for the data which are not very well behaved, it sort of seems to stop moving and then it just explodes and starts again and moves in some strange places. It's very exciting. Yeah, you can stop it and pause it and all, of course, but you can keep looking at it. So you can see here that with this sort of projection, in fact, although in those small dimensions when we directly project through LDA and through the OPCA, those points are quite mixed. But in the original large space, the language is actually quite well separated in terms of the distance. So, we can see that, these are amazingly uniform blobs, as it were. And you can see that the language is in the original large space, because of course when we just turn the space, we lose all the, it's a little bit like looking at the stars, that we lose the vision of how far the stars are actually in dimension, which we cannot perceive, because the dimension which is going away from us. So if we do the LDA or PCA transformation, we lose the information about the other type of distances. We are as if looking at the space from one direction and cannot perceive the distance. But of course there is a lot of distance information in the other dimensions, and we can see that in this, what am I running? TSNE, that those data are actually quite far apart. And here there is this interesting blob containing, I can label it by language, containing somewhat surprisingly Hindi and Manipuri and Lushai and Angami. And so here, for example, in the real distances, well, I can maybe run it in 2D. In the real distances, the Angami and other Naga languages actually and Manipuri are lumped together in a separate cloud. For some reason Bengali is very separate, but it's because we have so many Bengali speakers that again it tries to push the Bengali crowd far away, because it's satisfied when it, of course it has to kind of get this distance good on average. And if there is a lot of close sort of similarities between Bengali embeddings, it tries to push it far away, so that overall kind of match between the distances is maintained. What's kind of the fact that these are too far and these are too far is not so important, but the fact that they are all lumped together, that these clouds are sort of essentially single color, it means that in the multidimensional space they are actually quite close together, which is quite amazing that this technique, the recordings we did, regardless recording conditions, regardless of many other things, is actually working fine.
So the model is kind of having a hard time only with northeastern languages.
And rather surprisingly, Hindi is kind of, in these visualizations, tend to sort of pop up among the languages. So again, it might be because it has similar number of speakers, so the projection is not rewarded for separating Hindi from the other languages as much as it's rewarded to separating, let's say, English recordings. It's as if, calculates all the possible distances between all the possible points in the original space and in this space, and then tries to sort of match them, correlate them as well as it can. And uses different algorithms to do that. But of course, when you have many combinations within the Bengali class, it favors to do a good job there, and little bit it doesn't matter hugely, and of course tries to put Hindi far from Bengali and all that. But But in the first place, what's sort of astonishing that these colors are not present in any of these transformations we are running here in the embedding projector. These colors are not given as an information for the whatever visualizing thing. So all of the fact that these clouds are single colored, it's completely emergent. It's completely comes from the way how we analyze the thing. So it's quite astonishing that, of course, well, LID have those things. So LID is trying to push them apart.
It's not here.
But this is not, okay, these are raw embeddings, so there is no actually LID transformation applied on these. So it's really quite impressive. I'm saying that it's quite impressive. I'm sort of generally impressed myself when we came up with this idea sometimes, I don't know, second half of last week or something like that, that we'll do this recording thing. One of the major plans was, we thought it might work, we'll see, but most likely it will not. And it's going to be hopefully very instructive failure. You can analyze that, why does it not work? So I was actually quite skeptical. In the last maybe thing for the future. I'm not gonna try it because I'm sort of not used to be coding hugely that way. But this Jupyter notebook, you probably know that, also sort of has the Gemini AI, the large language model, plugged into that. So you can, of course, try to edit the code yourself if you feel like it, and of course you can. This is relatively simple code, so you can sort of learn from it, hopefully. But also, you can use the Gemini, and under the bit of code, you can add your own code if you want. And here you can either start typing the code if you are so inclined, or press generate here. And well, you have to probably commit something again if you're. And you can ask thing here. I don't know. We colored this by gender. What was there to color it? Yeah. Please. Well, I'm polite. Please. Oh no. Maybe let's do it without. You know. Do the same with coloring by city, and when you press it and you are lucky, it will generate the code. Handle cases where city might be missing. Okay. We'll see. And when we press it, it works. It complains about something, but it has still colored things by cities, you know. And of course you can go further. Next step, explain error. And in this particular button, explain error is a good one, because you know, if you are sort of taking some programming classes and your teacher who is teaching you programming, you tell her or him that you are using this Gemini to code, they might be sort of angry. But when you tell them that you often use the explain error button, they are going to be very impressed and very happy, because that's the way how we learn programming. Very few people nowadays program from scratch. I've been programming since I was 14. I got my first computer. What am I, 50 for 40 years? Almost daily. And I've very rarely start with a blank thing. I just take some code from somewhere and start tweaking it, and actually use ChatGPT nowadays to program for me anyway. So there is no shame in that. But of course it's very useful to, at the beginning, to learn the basics, mostly to learn how to think like a computer does, or like the programming language does. All the grammar of that and syntax, that's secondary. That comes, that's the AI can give that to you, but sort of getting to ask right questions here is very cool as well. So yeah, so we are kind of finishing our presence. You feel free to stay. I don't know. Shouldn't talk for the other people here. Somebody might kick you out, but you know, feel free to spend, you know, time with this. So tomorrow, I guess we meet again at 9:30, and we will have some sort of. It's going to be a lecture. We can call it a lecture, but I am much more interested in having a discussion. We will a little bit talk maybe about, in particular, you know, promises and limitations of these methods. We've talked about them quite a lot. We will just try to summarize them, put them on the sort of few slides, so you will have them for the future reference. And then in the afternoon, for those of you who are interested, we will have this 1 hour sort of exam thing. How many of you want to do exam? Can you put your hands up? Okay. Just to know how many exams we should print out. 15 or something, 10. And then we will kind of correct it straight afterwards, and yeah.
Yeah, those who want to get the grade card, actually exam is not optional. So how many of you want to have the grade card is the question.
Right question, yes, exactly. Mm-hmm. But anyway, and then we will correct the exam, so we will make them quickly correctable. And yeah, I guess I can tell the form of the exam. I don't know. And of course, these are very big differences between different sort of pedagogical or educational institutions, how the exams are run. but we will generate, well, write, I don't know, 30 or so, maybe questions or statements related to what we were talking about. And your job is going to be to say whether the statement is true or false. That's all. So this is, so if you, oh, I'm not sure if I uploaded today's slides. If not, I will upload them now. I'll check.
One is uploaded morning, one is at least.
Okay, so I will upload the afternoon one.
And then also like an exam is only applicable for, I mean, you can only have grade card if you have attending it offline. Online, because IIT Guwahati does not offer any grades online.
But I think I granted the access to, I invited, so does everybody, like, can nobody access the slides? Or is it that only few people who cannot access the slides? Few people. So what I did was I opened the Google, what is it called? Drive or whatever it's called.
We use the emails.
Wait a second, I used the email addresses you provided to invite you. So please send an email address of yours to the WhatsApp. If you cannot access it, then I'll add you as I'll give you access to that, okay? Because if there was any typo in the email address or something like that, I just copied all email addresses and put them on block.
Yeah. So any questions from the online participants?
So now all the lectures and even some slides for tutorials, at least for this one. Well, yesterday one's uploaded. We will not be probably producing the slides for today's tutorial because essentially all the notes are in the Jupyter notebook. All the steps are sort of covered there, so well, we will just replicate them in another format.